I have a pretest that's really a post-test. This is all about Physics 205, and it's going to help you remember the key concepts that we're going to need to talk about voltage.
Oh boy.
You thought you could just forget 205, like you forgot that poetry class. That's not the way it works. You're thinking about the ideas that are important as we start our study of voltage. Okay? Let's go over it together. The first thing you notice about this boulder is that it's a boulder in Hollywood. It's about 6 meters tall and it only has a mass of 10 kilograms. It's clearly made of styrofoam. It's just a visual. Now, we're going to be dealing with the idea of energy. And you remember that we had different kinds of energy. We had kinetic energy. That was 1/2 mv squared. Now m is always positive and v squared is always positive. So this is always a positive number. And it's not a vector. There's no kinetic energy east or kinetic energy west. They're just kinetic energy. You either got some or you don't got some. It's like paint or money. And so you can think of this as a paint bucket or a bank, either way, that you store that energy in. Now we also, in the case of 205 problems, we have gravitational potential energy, mgh. And again, mass is positive, g is 9.8, the gravitational field strength. And if we choose the lowest point in our problem to be 0, our height is always positive. So again, if I make that choice of height, this is always a positive quantity, and I can put it in that bucket. And then we add those together, the kinetic and whatever potential we have, to define a new bucket that we call the total mechanical energy, or sometimes we call it mechanical energy, often we call it just total energy. Now, if Rand, a friend of mine, lifts that rock, and he's going to lift it a very special way. He's going to start from rest. He's going to push it at a slow, constant velocity, and then he's going to stop it at the top. Okay? Now, the question is, how hard is he going to have to push? The weight of that block is 100 newtons. That's just m times g. If he wants to push it at a slow, constant velocity, by constant velocity I mean 0 acceleration, how hard does he have to push? Greater than 100, equal to 100, or less than 100 newtons? Equal. Now he has to push a little bit harder to get it started, a little bit less to get it stopped at the top. But if I average over the whole push, it's on average 100 newtons. Now, he's pushing in the same direction as it's going. You remember our definition of Verk from 205 was kind of messy. It had 3 parts. It was positive force times the distance, if those two were in the same direction. It was minus force times the distance, if those two were in opposite directions. And it was 0 if those two were perpendicular. Now in this case, Rand, the external agent, is pushing up and it's moving up. And so he does positive Verk. And that Verk is just plus the force times the distance. The force is 100, the distance is 12 meters, and that means he has done a positive 1200 joules of Verk. Now, in 205, the grand high Verk energy equation was that the energy in the morning was always equal to the energy at night, except when it wasn't. And it wasn't whenever there was an external agent doing Verk, either positive or negative, on our system. Now I can write this a more useful way when I'm talking about voltage. And that is that Verk external is what changes total energy. Right? If I bring the E initial over here, it becomes a minus, and final minus initial is just a change. Now, if I've got two different kinds of buckets, that change, whoops, spell it right, Verk external, that change in total energy can either happen as a change in kinetic energy, or it can happen in a change in gravitational potential energy. Now in this problem, Rand started from rest, no kinetic energy, and he ends up at rest, no kinetic energy. So in that case, the special way he moved it, there was no change to this bucket. And all the Verk showed up. If I look at where that Verk went, it went into filling the total bucket, but the kinetic energy bucket didn't fill, so it must have gone into gravitational potential energy. And that's how we got our formula for gravitational potential energy. This was the force that he pushed with, the weight, and that's how far he pushed, the height. Now, folks, as he was pushing that rock, he was cocking a gravitational spring. He was storing gravitational energy. Now think about the gravitational field. The gravitational field's pointing down, and he's pushing that boulder against that field, storing energy. Now that energy we call potential energy. Why? Because it's got the potential to fall. Remember, energy is the capacity to do damage. If that boulder's at the top of this cliff and you're walking at the bottom of the cliff, you feel nervous. You say, whoa, that's a potential disaster. Okay? And all it takes is for Rand to just kick that rock and go home. Now, if he kicks the rock and goes home, he's not doing any Verk. He's just getting it started, and then he walks away. So if there's no Verk being done, there's no change in the total energy bucket. Where does that energy go? Well, it sloshes over to the kinetic energy bucket. Folks, that is the problem that we'll be solving over and over and over again this next week with voltage. Only instead of taking gravitational potential energy and turning it into kinetic energy, we're going to be taking electric potential energy and turning it into kinetic energy. And that's a very important thing that happens all around us. That's why we're interested in it. Okay, so think about that. Memorize that. Relish the fact that that is trivial, because that is exactly the same as what we're going to do with voltage. And if you can see how trivial this is, I can show you how trivial voltage is. Okay? Whoa, that's different. This is a positive plate and a negative plate. Positive charge, negative charge. The electric field lines between them are parallel. And they go from the positive plate to the negative plate. Oh, folks, we didn't do the second half of the pretest, did we? You turned over your pretest and you found that we had lied to you. The bottom of the cliff wasn't the bottom of the cliff, it was just a ledge. The bottom of the cliff was way down below. Did that change any of your answers on the first part of the problem? No. That's another important fact, is that in 205 problems, all we ever cared about was the change in elevation. It didn't matter whether we put the zero of height at sea level at Los Angeles, or whether we put it at Main Street, Bozeman, which was 4,800 above sea level. We got the same answers either way, because we only cared about the change in elevation between the top floor and the bottom floor of the building. In the same way, we only ever care about the change in voltage. And so we'll see that that's an important parallel. Now, between these plates, the electric field is going to be the same size everywhere. And it's always going to be pointing from the positive plate to the negative plate. Now, folks, tip your head. Instead of electric field, think of that as a gravitational field. Think of this as the bottom of the cliff and this is the top of the cliff. It's the same problem. Only instead of a gravitational field pointing towards the bottom of the cliff, it's an electric field. Now, I take a +1 Coulomb test charge. Think of that as the boulder. Where does that +1 want to be? Does it want to be next to this positive plate? No, it wants to be next to this negative plate. It wants to be at the bottom of the cliff. Just like the boulder wants to be at the bottom of the cliff. Now, if this hand pushes that 1 Coulomb from A to B, it's pushing it against the electric field. Just like lifting the boulder is against the gravitational field. It's taking that 1 Coulomb where it doesn't want to be. And in the process, the hand has to do positive Verk. Now what's happening is the hand is cocking the spring. But this time it's not a gravitational spring, it's an electric spring. Okay? If I go back to this formula here, energy initial equals energy final except when Verk is done, and I write it as Verk is changing the total energy, in this case, instead of gravitational energy, I'm going to have electric potential energy. Now typically in these problems, we're moving protons or electrons. And their masses are so tiny that we don't have to worry about any change in gravitational potential energy. And so the only two buckets that we typically deal with are kinetic and electric potential. Now if this hand pushes in such a way that it starts at rest, it pushes with a slow, constant velocity, and then stops at B. It goes from rest to rest. The change in kinetic energy is 0. And that allows me to calculate how much electrical energy was stored by the external force. That's how much Verk you did. Okay? So, if I do it in such a way that there's no change in kinetic energy, the Verk done by the hand is equal to the stored electrical energy as I move that charge from A to B. Okay? Now, are we all with me? Now, because that charge doesn't want to go there, I'm going to have to push with all I've got to get it there and stop. That means I'm pushing in the same direction it's going. That's positive Verk. Now let's say, for sake of argument, that I had to do 100 joules of positive Verk to get that 1 Coulomb from A to B. I just made that number up. Work with me. Okay? What if instead of bringing 1 Coulomb from A to B, I brought 2 Coulombs from A to B? How much Verk would I have to do? Double. Well, if I look at my definition of electric field, the electric field between the plates doesn't depend on what I'm bringing from A to B. If I double the charge that I'm bringing from A to B, I'm going to double the force of the electric force. Well, that's the force that I'm fighting to bring it across at constant velocity. So if I'm fighting fighting a force that's twice as big, I have to push twice as hard. That means I have to do twice as much Verk, or 200 joules. Now, folks, because I'm moving it from rest to rest, the Verk I do, which just doubled, is equal to the energy stored, which just doubled. Okay, I just stored 200 joules. Now what if I bring 5 coulombs across? How much energy do I store? 500 joules. What if I bring 10 coulombs across? How much energy do I store? 1,000 joules. Here's a tricky one. What about a minus 1 coulomb? Well, a minus 1 coulomb doesn't want to be by the negative plate. If I let go of it, it's just going to race. It's just going to race towards the positive plate. But I want to move this charge from rest at A to rest at B. So that means if it wants to fly that way, I got to hold it back. And I got to push this way while it's moving that way. What kind of arc am I doing? Negative arc. And so I would store minus 100 joules. Now what does that mean? When a change in something is negative, what does that mean? When the change in your bank account is negative, what does it mean? Ooh, money's draining out the bottom of your account. Probably someone's stealing from you, okay? Not that you're spending. Maybe it's your spending. Okay, how do I write this in general? Well, I say that I do 100 joules of Vert plus 100 for each 1 coulomb. And then I multiply that by how many coulombs I actually move from A to B. If I move 5 coulombs, then I multiply this by 5 and I get 500 joules. Okay? Now this thing here, the joules for each coulomb, we call the voltage difference. Okay? The electric voltage difference. And it tells me how much electric potential energy is stored if I know how much charge is brought from point A to point B. Now folks, this is a rate. Okay, if I say that at the wall here we've got 120 volts, what I mean when I say volts is joules for each coulomb. We call it volts to just honor a dead physics professor. One of the most noble things you can do with your life. Okay? But what we really mean is at 120 volts, every coulomb that passes through that outlet is going to be delivered, is going to be given 120 joules. Now if you plug up your stereo to that and turn it on, that energy that's delivered to the coulombs is used up in your stereo. We'll talk about that after spring break. But here's the thing. The voltage is just the rate. It's how much energy you're going to be using for each coulomb that passes through your stereo. Well, if you leave the stereo on all day, turn it up loud, you're going to have a lot of coulombs going through your stereo in the course of that day. For each coulomb that goes through, you're going to be paying for 120 joules of electrical energy. Okay? If you just turn on the stereo and you say, oh, I don't like that song, and you turn it off, your voltage is still going to be 120 volts, 120 joules for each coulomb, but you only left that stereo on long enough for a tiny fraction of a coulomb to pass through. So you're not going to pay for very much energy. Okay? That's the idea. That's the idea. Okay? So electric voltage. It's the change in potential energy if I take 1 coulomb of charge from A to B. Now, if I take that 1 coulomb of charge from rest to rest, so that I don't change the kinetic energy bucket, I can also think of the change in potential energy as the Vert that the external agent has to do. So there's 2 ways of conceptually viewing this. How much did my potential energy bucket fill? Or how much Vert did an external agent have to do? Either one of those will give you the voltage, as long as this thing that you're moving from A to B is 1 coulomb. It's a rate just like the electric field. If you tell me how much 1 gallon of gas costs, I can tell you how much any car full of gas is going to cost. You got 15 gallons, I can tell you how much that costs, as long as I know how much it is per gallon. This is how much energy per coulomb, not per gallon, per coulomb.